learn to look at the world, learn to understand what shortcomings you might have, what you're strong at, and just accept them and decide how you can work around it and don't let it bother you and don't think that you're the only person. Just the world is out there and if as long as you're working at it, I think what is oh yeah, the life unconsidered is not worth living. Just don't retreat. A lot of people they get out of high school and they just retreat and they stop thinking. And you guys have all made the decision to go to college, and I hope that that's the biggest thing that you learn. It's critical thinking, skepticism, but also that you can always keep improving yourself and fine tuning your viewpoint. And uh, it's just a big adventure. Okay, so looks like we're filling in, and once again, they say that the first casualty, well, the first casualty of war is the truth, and the first casualty of battle is the plan. And so we had a get ready for the class assignment about and purchasing the cat of Sims, and then of course all you had to do, um, strictly speaking, was to submit a screenshot showing you bought it, right? Fine. I mean, I can't complain. But of course, and maybe because at the beginning of the semester, excuse me, Adobe was giving the Ket people some crap. And so for a while there, it couldn't be installed, and we haven't really used it much. And so it kind of fell by the wayside. So I got several, well, yesterday, I don't know, I kind of like, I had, I played volleyball in the morning and I work all weekend. And so I have my half a day where I chill. Then I had my basic electronics class it goes from 2 o'clock till 6 o'clock. And it actually went till 7 because they were asking me questions about FM radio and frequency modulation. And I was trying to, it was all stuff I was doing while I was in Korea. And it was kind of bumming me out that I couldn't, I've, even just in a few short years, it took me a while to get back up to speed. But anyways, I was like crashed in front of my TV by about 8 o'clock, and I noticed this morning messages. Somebody texted me right after I finished turning off my computer. Sorry, I just crawled into bed and ignored the world. So, anyways, is anybody? I sent a message out an hour or two ago about this. It was, and this link was live in the announcement. So, the big deal is to get this Air software development kit installed. Now, it looks like this. Yeah, unfortunately, this doesn't run on something like an iPad, but it should run on a Surface, Microsoft Surface. So this here, the runtime environment is free. I see pricing and such up here. But this is just, excuse me, this is what happens is these cat sims are like, I don't know if you know what JavaScript is, but they're sort of quasi computer programs. So it's just like a script or a set of directions. And what's running on your computer is this thing called Adobe Air, and then it's waiting for you to tell it to give it the script, the set of instructions, and that's what you see here. It's just a set of instructions for it. It says, all right, draw this on the screen, do this, do that. But the thing that's actually operating on your computer is this Air runtime. So I wanted to make sure get that out of the way first. I'm not seeing anybody, hey, I don't have it running yet. So apparently we figured it out. We all can make this sim run. I realized after we did our marble track, there is an air track sim, but I thought it was a lot more fun to roll marbles personally, but it could just be me. Okay, so nobody's saying anything, so I have to assume it's all working. All right. So one thing I wanted to go over too is I would assume you saw my announcements because I'd said at the end of the last class that I would give you a number to know what is the expected value that you're going to get when you calculate the acceleration of gravity from your marble data, or the class, our marble data, and I warned you that you were going to be disappointed in the answer. So our expected value, I believe, yeah, it should have been 980. Yeah, but we end up getting, let's see, uh, I was working with our colleague George after class last week, so we were looking in Excel, which I'd like to use from now on. Excuse me. And so we ended up, which you guys should get something similar, because yeah, we did it in class, 69.7, which is well, first of all, wait a minute, give me a minute. That's not right, something just there's something not right. Not we wouldn't expect, and I have to remember what was the angle. What was the angle of the? Oh, I thought I put it in here. Oh, see, not prepared for class again. All right. Right. So we had approximately 22, like 2.8 centimeters, 2.8 centimeters, and about 28 centimeters long. Divide, and then if I take the inverse tan, I'm looking at my calculator, 5.7 degrees. So so it's 5.7 degrees. So we said that the expected value is going to be the sine of that, right? Yep. So sine of that, and that's going to be times the actual acceleration of gravity, and that's 97.5. Okay. So our expected slope, expected acceleration on the ramp is supposed to be 97.5. There it is. Oh, and in fact, right, so it'll be right here, this one, this blue line here. And, but I don't think I did a fit to that, no. So anyways, we expect to be 97.5, but the reason it's not is because, and I think I talked about it. Michael, sorry I missed that. And finally, okay, you think okay, so let's see I'll keep talking a little bit and let Michael tinker a little bit, and then Michael, what operating system do you have? OS X or Windows? Is he still here? He might have gotten punted. Yeah, he's here. Because I just want to know if you and Ghazal have the same, or Ghazal had OS X. So anybody who has OS X that was able to successfully install it, or maybe you haven't. I mean, I'm sorry, I wouldn't have plowed ahead. Okay, Michael, which operating system do you have? or you just get it? You haven't installed it yet. Windows. Okay, so I don't. My wife's PowerBook died the other day. We're waiting for a stimulus check to buy her a new one. So has anybody else in the class been able to get it to work on their Mac?
I wasn't able to get it to work on my Mac, even installing the
So
Air Quick thing.
so
Okay.
I
what I
did that
did is
too.
Wait,
sorry.
oh,
Well, you can try when you highlight it from the file, you go to the top and hit file at the top, and then you select open with. And if
oh.
you have the Air installed, then it should give you that option to click the Air, and then it should open up like that. That's how it worked for me.
Now, Jenny, is that in with a Mac?
Yes.
Oh, really? So this
Mhm.
thing, normally the Mac knows what to use, so I know what she's saying. So, right, I can model it anyway. I can't do the
If I can say
exact.
one thing too, for my Mac, I had like a security system in place, and it wouldn't let me download Mac
Right.
the Air. And also, what helped me out too is that I downloaded the whole zip file, and then it downloaded to my computer, and I picked the file from my desktop instead of the actual website.
Right. So that's right. See, these are all the script files here. And well, actually, they seem to be installer files, but we need to talk about oh yeah. So well, first of all, let's just do what Jenny said. You right mouse click on it, and it won't look exactly the same, but you see open with. So somehow there's one chance that if you have installed the SDK, yeah, if you've installed the SDK successfully, and but you still can't get it to run, this is what Jenny's solution was. And then you'll hopefully see something like this, and you tell it to always use that, and then from now on, when you double click on that, it'll work. Oh, well, first of all, it's installing it. Okay, so wait, so Jenny, I guess this is fine to get it to go to install it. Oh, run now. So it already exists. So where does it keep once it's installed, where do they keep, that could be another thing. Where does it keep it? Here we go. Property. No. Well, this stinks. I don't remember well, in a Mac, Jenny, does it install it into the applications folder?
I'm not sure, but I had to for each of the files. I had to do that to open them because that's the only way
Right.
I was able to open them.
I see. Right. I understand. That's it. Right. So, right. Thanks, Jenny. Now I got it. That what the ultimate answer is then you download this zip file, right? And I don't know if I still have the actual zip file. Let's take a look here. I may have, but you get a zip file, and I don't know, and mine I downloaded before they had issues, so maybe it had the Air installer. Okay, open my download folder and search download zip. And oh my goodness gracious, look at all those. I gotta do some. Uh, so wait a minute, that's not a good search term. I think VPL, huh? VPL. There it is. So in principle, you download something like this. And yeah, the SDK is not here, right? So then you extract this somewhere, and I just put it, because I use it with lab class, I put them here. So right. So let's show you, let me model this for you. So I'll take this and I'll rename this, save. So now wherever you want to put this folder, it's this is where Windows is caught up to Macintoshes. You just take it and drag it where you want it to be, and there you go. Now you see that this thing has an icon because I have installed this guy here, right? So this downloads you an executable. And for a Mac, let's see what it, oh, it's a disk image. Okay. So for a Mac, I can download this. It won't do anything. Questions. Oh yeah, I never hit people with late fees. Yeah, that's fine. Don't worry about it. I mean, in the case of pre-labs, it's nice I try to set up the pre-labs so that they get us up to speed. That's all. Hold on a minute. I got something going on here. Yeah. Somebody. Right. No cell. I mean, I don't even stress if students use their cell phones in class, as long as they're not disturbing others. Let's see. Let's go back to the download folder. And yeah, see now the file that Windows recognizes is this application file. In a Mac, you'd see this DMG, the disk image. You double click that, and it'll have like an installer looking icon, I would bet. And OS X, Jenny could tell us about that, and it may even have like README or something like that. Correct? Do you remember, Jenny?
I don't remember. Let me double check right now.
Okay, yeah, you might have the DMG file. Oh yeah, right. If you don't mind, you could share your screen, and then open the DMG file, and then once it's on a window on your computer, share your screen so the other Mac people can
Okay,
see it.
Professor, I was able to open it. So I downloaded the full set where it says download for Windows. I didn't click on that because I don't have Windows, but I downloaded that Windows and that seemed to work.
Oh, really? Yeah, it should. The full set, yeah, because those are in principle just text files. But that's interesting. Let's go. Where is it? Now this is the physics classroom. Let's see. And yeah, of course you want to be a little hesitant on that one. So let's see, full set. And right now let's try looking at the installation instructions again. So once you have
Yeah, I think what Jenny said is the best thing to work it out.
is to
It's whenever you know how you send us the two links where it says to download the air, and then in the bottom it says there's something that you can click. It says here. It's
yeah.
gonna take you to this page. I can
Oh, right. That's right. In that message I sent out, right. Oh, there's Ghazal's sharing her screen. So you can double click. Oh, how do I maximize her? Oh yeah, there we go. Pin.
So right here it says VPL full set Windows.
Yeah.
Yeah, that one. If everyone just downloads that, and then from there it's just gonna show all of them. It
Yeah.
opens faster.
Okay. But it looks like, what do you have? Is that a Mac, huh? Okay,
Yeah, it's a
right.
MacBook,
Oh,
but
so it
this
did
is
that.
still working.
Gotcha. I got you. Very good. Thank you. Right.
Mhm.
So it's like I thought. The the zip file itself, even though it says Windows, it has where are they? I've got it down. Yeah, here it is. I would bet. Let's see. These could be text files. Let's take a peek at one. Open with, and I just have to satisfy my curiosity. It's not important for you guys to do this. Oh no, it isn't. But somehow it doesn't seem to matter because it makes sense. What's happening is that once you have the Adobe SDK, the Air running in the background, it's no longer Windows or OS X that needs to understand these Air files. It's the Adobe Air itself. Yeah, that makes sense. Okay, but thanks for that, Gonzalo. That probably makes, I guess, was Jennifer Flores. That makes her feel safer about double clicking one of those now. Okay, we're getting there. Let's make sure we all have it up and running. It's fine. It's obvious that we should have spent some time on this sooner, and it's my fault. So don't worry about it. And why not? Let's make it official while we're waiting for people to find new problems. Assignments. Okay. And there it is. Can I just do it right here? Like the important part, huh? What, is 24 hours enough? Of course, how about next week, Dr. H? And because then that didn't give you any chance to play with it, we will even delay this 24 hours because I'd like you to write up a description of the apparatus. So we'll delay the lab day logbook submission. See, aren't I a great guy? I'm also too much of a pushover, probably. Actually, yes and no. You could ask my kids about that. I believe in faraway fences that are very, very high. So lots of leeway. But when I say there's a place you can't cross, I usually mean it. But that doesn't happen too often. All right. So anybody still having issues? Oops, I lost the chat window. Where'd it go? There it is. Wow, that's weird. Why is it empty? Anybody having issues still getting the cat to work? Looks like we're on board. Okay, well, I will stop again if necessary. Now, of course, I got to remember. Oh, yeah. So, I was saying, right. So I was playing around using our data here because this is last semester we did this in 2100. Excuse me. And so now I just created a new tab for our data here. And what's going on is that you're having sort of a combination of sliding and rolling for the marble, but it's really not sliding. We just think of the sliding part as the center of the ball is moving down the ramp, but it's the marble itself is rolling. So if we were to have, say, well, the air track is the best because then you have a sled, it's gliding on a cushion of air, so it's got very little friction. So if we were in the real world, in a real classroom, we would get a very good number for the acceleration of gravity this way. And I was looking over your lab manual, and it's a really nice progression to make it to this point. After you do measurements and errors, then there's the ticker tape lab. Then there's using the air track, having the object move on the air track at a constant speed. And then there's doing what we did. And then there's actually, they have an apparatus in the 1570 lab where you actually drop something straight down, and it's really, I like it a lot, but it's difficult for us to do all that from home like this. And it's a combination of me not having faith in my colleagues who wrote that manual, which your manual is one of the most recently written up ones by, in fact, my colleague in my research group, Ricardo DeSalvo, who's a very smart guy and an experimentalist. But I'm trying to recover from my mistake there and try to teach you some simple stuff, just to give you an appreciation of what physicists do, and hopefully somehow you can translate it out to the way you look at the real world. But anyways, we sort of, the equations that we talked about and the acceleration of gravity in general, before you talk about rolling motion, it's just about like some object. If you let it go, it falls, and if you set it on a ramp, it slides down the ramp. But it achieving something with zero friction is very difficult. Air tracks are very expensive things, so we were stuck with a toilet paper roll. I mean, well, paper towel roll, but never let the truth get in the way of a good story. Um, and we used a marble, but the marble is rolling, and we don't know anything about rolling energy. And we get a number, and we were like disappointed because it's about 2/3 of what we expected. And so, well, you figure, well, this is 1570 lab, and I guess we're not expected to do a good enough job. But what I did is then I found the equation here and what the velocity should be at the bottom of the ramp for a given starting position. And then I cobbled up this spreadsheet to get the predicted velocity. And that is, let me see. Yeah, here it is, the green line. And the problem is that this is expressed not as a function. What did we were doing time and velocity, so I had to come up with a fit to that actually to get the acceleration right, because it's formulated using this energy formulation, which is, I don't know if you'll ever get to it in class, and I don't know if it's super important to go through that for a 1570 student. But anyways, I created a y equals mx plus b to double check exactly what that slope is, because that's what I need to compare to my results. So the red line here is our data. There's two green lines actually there. One of them has dots in it. And the only difference between them is the y-intercept. And so our data doesn't have a 0 y-intercept, which you would expect here. And it's no big deal, because what counts is the slope. So I got a expected slope of 69.33, and you see all those digits. So now, as I said, George and I were working on this after class last week. And we ended up, and I think we did in Google Sheets as well, 69.75 basically. Well, that's pretty darn good, huh? Let's take a look here. So, and the percent error, just as, and this is again not something really was used in the real world, but it's familiar to you perhaps. So we'll say the expected minus the measured, and then we divide by the expected, and then oops, it didn't take. Yep, and then we multiply that by 100, and that's pretty darn good, huh? 0.6%. But let's before we get too excited, we should now we can figure out what's the plus minus on this slope. And when you do it with a ruler, you sort of lay the ruler on the dots, and then you try to see what's the biggest slope that will pass through all the error bars and which one's the less amount of slope. You see how the important thing is to get as close to the dots as possible and also pass through the error bars. So now there's this thing called a chi-square, and the chi-square is just simply the residual squared divided by the size of the error bars squared. And if you think about it for a minute, that means that the points that have a small error bar, like this point is, it told me let's go back. This is 0.46. Yeah, so blah, blah, blah. Yeah, so the plus minus, the error bar there is only 5. So the chi-square value for that one is 0.1. And then the guys that have bigger error bars, like here, 7 and it's 11, you see their chi-square number is very small. So when you do the sum, the ones with big error bars don't have as much of an effect on the sum. And then the other thing, and then the math is very heavy, the other thing about the chi-square is that now you say if it's a great fit, it would equal to 1. But as long as it's about less than say 10, or maybe, and sometimes I've only once seen it go below 1, and I'm still convinced I did something wrong. But if you're close to 1, you've done a pretty good job on your fit without any proof. And then how do we get the plus minus? We can use this to get the plus minus. And the way you do that is you want to see what would be the slope if chi-squared now equal to the minimum value plus 1. So in this case, 1.89, well, it's 1.9. So what if we say we want the chi-square, if we tell it, instead of minimizing it, we may learn, we'll see. I don't know if we'll get into this or not, this solver business. Yeah, I want to use Excel. Number one, I found out it's free for you guys. I didn't realize that for some reason. And number two, it's an important, if you can put this on your resume that you know how to use Excel, it will help you get a job. Now, instead of minimizing it, we tell it we want it to be, what did I say, 2.90. 2.90. And then we hit solve. And it got an answer. So that slope is larger. So this is our maximum slope. So we want to copy this. Copy. And then just paste the value. And now we want to tell solver to give us back the original number. So just minimize it. And there it is, 69. So you see the plus minus is actually kind of large, right? So if we do this, copy, paste the value, and now we see what's the difference. So this is the max slope. This is the best slope. And then this is the difference, which is going to be our plus minus. And this, guys, just take some few notes about this discussion. Don't sweat about getting this all down. I just wanted to show you some stuff. This is well beyond physics 1570. So this equals the max slope minus the best slope. So it's plus or minus basically 4. And we can say it's all, we don't need to find the minimum slope because because of the way chi-square is made and because we're close to the minimum, we can assume it's symmetric. That means that max slope is going to be best plus, in this case, 4, and min slope is going to be best slope minus 4. So that means then that our fractional error on our measurement, and then we want to put it into percent. So we'll call it percent error on measurement. It's too bad. What can I do with that? Percent error. I know what to do. Just quick and dirty solution here. Format. Wrap. There we go. So that would be, let's see, the fractional error, so it's going to be equal to the plus minus divided by the best fit line times 100. So you see that it's a 5.7% error on our measurement, plus minus 5.7%. So it's a big error. So we're just saying that this is what we think is the best, but of course, the actual number is inside of this big. It could be plus 4 or minus 4 of the best slope, but it's still pretty darn good that with a marble and a cardboard tube, that we did a great measurement of the acceleration of gravity. In fact, what I want to do, I want to go back. Remember, we culled down the data, and at some point, I'm going to use the original data with the breakfast cereal. And I still say bravo to the people who did that. I want to just see. I think we'll probably still get a good number, but of course the error bar will get much bigger. So I just really wanted to show you how we did. It's really remarkable how with this crude apparatus that if we're clever, we can get a good measurement. And this is a statistical measurement this way. And remember, that's because we really didn't know how to give a quantifiable estimate. We couldn't really estimate our errors on this. And so we used the range method to get us a plus or minus time. And we were able to get a plus or minus X because that one we could kind of figure out. But the rest of it, the time was heavily influenced by, like, if our fingers were like, if somebody's fingers were shaky, or if one time you rolled it, you didn't pay as much attention. These are things that are very difficult to quantify. So you just measure it a crap load of times, and that beats down these individual error bars. And then the graphing brings it down even more. So very good. We should all pat ourselves on the back. Very good. Okay. So let's get into what we're doing today. And so we need to talk about some definitions. So now we should be paying attention and writing everything down. So let's start with some basics here. Just getting my tablet ready here, my drawing tablet. So the first two things we need, and hopefully you got a sense of these from the pre-lab assignment. Oh, let's try purple. There's this momentum, and then there's kinetic energy. So momentum, and it has a symbol P, lowercase p. and it is a vector, so we have to worry about direction, is the mass of an object times its velocity. And there's no sines or cosines involved because m itself, mass, is what we call a scalar. So it's just a number. So if we multiply a vector times a scalar, we get another vector, but there's no worries about angles. Now, velocity, any vector can have three components or some subparts, and in x and y and z. But for physics 1570, I don't know if you guys will do projectiles, but for the time being, and just give me a minute. At most, in 1570, you may have to deal with Vx and Vy. And then you would say that V total, and this is just the Pythagorean theorem, for example, for the size of V. But for us, for momentum will always be one-dimensional. No. So that means that it's going to be most likely the x-axis, could be the y-axis, and then with only one dimension, direction, whoops, let's try that again. Direction is positive or negative. So it's pretty straightforward for you guys. Your momentum is and usually we say that positive is to the right and negative is to the left, right? Just like a number line. In fact, I think I'll move kinetic energy to the next page. Excuse me. Okay, now, so if we have m equal to 2.0 kilograms, and the velocity equals plus 5.0 meters per second. So we say P is equal to mv, in this case 2.0 kgs, and we always remember to put the sign. So this is going to be a positive 10, and let's see, 2 sig figs, kg meters per second. There's no special unit. And then let's call this M1 and V1, and then we could also say, all right, now I have mass 2 equals to 3.0 kg. And the speed of this guy is negative 3.0 meters per second. So the P of object 2 is going to be negative 9.0 kg meters per second. We always have to remember that there's going to be a plus or a minus, a direction. Okay. So next is kinetic energy. And this, I think you're asking me this. What I heard could definitely go on a mixtape.
Just the other side, please.
And if I still didn't understand what you said, but I know you were laughing a bit. So if you actually require a coherent answer from me, you better type it. I don't know what's up with your internet connection. Sorry to have a laugh at your expense. Right. So the next one is kinetic energy. Now, energy is a whole development of itself. Kinetic energy means it's also mechanical energy, but it's mechanical moving energy. You got to be careful because there's a thing called potential energy. Wow, how about horrible handwriting, huh? Mechanical or mechanical moving energy. So you can call it K, capital K, 1/2 mv squared. And doing everything in the energy formulation, and for example, that's what I was doing over here. See, there's your 1/2 mv squared. There's an expression for the rolling energy here on the right. I don't know if you guys can all see this. Oh, that doesn't work very well, does it? Hold on. But doing everything in the energy formulation is really nice because you see I can just add together the XYZ energy with the rolling energy. There is no worries about apples and oranges. And also see here there's a potential energy here, but that's a discussion for another time. But because the reason that you don't have to worry about apples and oranges is because energy and kinetic energy, any kind of energy, is a scalar. A scalar. So that means that there's no direction. And mathematically, that comes up because you're squaring the speed or the velocity. And now the units are joules. So this gets its own unit. And this is, oh yeah, we'll get into this in a minute. It's a Newton times a meter, which is kg meters per second squared times meters. So it's meters squared times kg divided by seconds squared. And you can kind of see it here because 1/2 times kg times meters per second squared. Excuse me. Well, that's weird. Oh, somebody drawing on the screen? I think I have it set up so you're going to get busted. Let me make sure. Yeah, I have it. See, it says hide names of annotators, but your name stays. Well, I guess it didn't stay. I thought I saw a name. Let's see. K, it could be 0. But can't be negative. There can be negative potential energies, but we're not going to get into that. And this business of never being negative has some implications. We'll get into it when we talk about conservation of momentum and conservation of kinetic energy. You might recognize those words from definitions of elastic and inelastic collisions. So next step now is to relate KE and P to force. So we're just finished speaking about kinetic energy, so we'll start there. So if we take a force and let's say we have an object and we push on it. And pencils, huh? Let's use a pencil. So we have, it's on a surface, but there's no friction So there's like no air. It's resting on the ground. Or it's sliding around. It's sliding on the ground. So no gravity. No force of gravity. So no force of gravity. All it knows about is that we got this block and we're pushing on it. And we push on it for a certain amount of distance. You get a change in kinetic energy. And usually we're going to just say it started from rest. So it's just simply F times D equals kinetic energy. But it's always good to remember that there might be a change involved. So always keep that in mind. This is also defined as a quantity called work. And only in the situation that I showed you right here does it have a change in kinetic energy. So just to be safe, I don't know if it's super important for 1570, but it only FD equal delta K only only, give me a minute, no friction, yeah. And in fact, gravity, give me a minute, let me think. It's not that if you have gravity, you can have, okay, right, I got it. No friction and plus if where's the gravity? Right, got it. Stupid. And yeah, free fall. What's called free fall. And that just means that only it's no friction. It has to be no friction. And it's either F push or free fall. That's it. Good. Now I got it. So free fall just means only gravity. I set up this example here just to help you to understand the basic principle. But in the general sense, you get a change in kinetic energy. Either you push it and there's no friction, or you set something like you throw it up into the air or you drop it and only gravity is working on it. Then you get a change in kinetic energy. And in fact, I just realized something that I should have done. Let's take a look at our examples here. Oops, well, that's fine. Copy. So let's do a little digression here. Paste. And first of all, we need to get rid of this. And this. And let's, I just want to get rid of those blue marks. There we go. All right, so now, clear it again. Back to being a mouse. I just want to make this smaller, that's all. I'll put those notes from before back up, never fear. Okay, so let's take a look here. So now we have, let's do KE of M1. So that's 1/2 M1 V1 squared equals 1/2 2.0 kgs times 5.0 meters per second squared. So if I'm not mistaken, that should be 25 joules. 1/2, it's just 1 times 5 squared is 25. Yeah. And I remind you that kg meters squared per second squared is joules. Now, KE M2 is 1/2 of 3.0 kgs times minus 3.0 meters per second squared. So we have 9 here times 9 is 27. So 1/2 of 27, I believe, is 13.5. So we cheat a little bit because that's more than 2 sig figs. Notice it's positive, right? Kinetic energy is always positive. So we also notice that that object 1 has a higher kinetic energy than object 2, even though object 2 had a larger momentum. So then let's see if I can save this here. So we want to relate, let's get this out of here. And all right, I can't do a cut because then I'll lose the footer there. So let's put this here for temporarily. Get rid of this. Get rid of this. So let's see if I can pull this off. There we go. There it is. Okay. So then we define kinetic energy, and then we added the calculations of kinetic energy for our 2 objects from earlier. And then let's return to our discussion here about kinetic energy and force. This way I can just make it smaller. So if I apply a force over a distance, there's no friction if I'm doing the horizontal direction. So only F push, or there's no friction and I'm in free fall, meaning the only force is gravity. We end up with a certain change of kinetic energy, which if you think about it, basically means a change in speed. And that's how it relates to the marble, because I can use the energy formulation to calculate what its speed will be at the bottom of the ramp. And once you go through the excruciating process of using the time and speed, time, position, and time and acceleration equations, you get, I always tell students when I start teaching them, but I don't know if you got energy formulation. So if that comes up, we'll come back to this. For now, the important thing for us is that kinetic energy is a property of motion and of a mass and speed of an object, and that how it relates to force. Now, the other quantity we have to relate time is the momentum. Well, let's go back to, I like the purple one. Always my daughter's favorite color when she was little. Excuse me. So now momentum momentum and force. And this actually is the one that you can relate to the most. So if we take force and multiply it by the amount of time we apply the force, this equals the change in momentum. Conditions apply. I mean, you could have friction. It gets a little more complicated, but for the time being, no friction. And it's only so it's either only push or pull horizontally, or, so either or, gravity or free fall. That's right. Free fall implies only force of gravity. Free fall. Only gravity. Now, it could be object is traveling upwards as well. And in the case of gravity, it's always downwards. So we have to remember that the force is going to have a direction, and for us, it's plus. So we have to always keep in mind there's a plus or a minus for direction. So that delta P will either be positive or negative. And remember that since P is equal to mv, but mass is a property of an object, so it can't change. So we're basically talking about, once again, just like I said earlier, the change in the speed. So of course, this will also be positive or negative, the delta V. And the easiest way to think about this is, say, an airbag in a car. So just yell at me if you want me to go back. Oops, I don't want to do that. I'm going to duplicate this. Okay, so F delta T equals M delta V. So let's say that you're going at, I'm trying to remember what, 60 miles an hour. I think that 60 miles an hour is about, so let's say we're going 10 meters per second in our car. And we hit a brick wall. And let's think about our heads. So, so our head's about the weight of a bowling ball, which I think is about 5 kilograms. So mass of a head, let's say, is 5 kgs. And at t equals 0, when we hit the brick wall, our the velocity of our head is equal to 10 meters per second. And when it hits the steering wheel, or so we call this velocity of head initial, and at some point it's going to, at t equals later on, when our head hits the steering wheel, it's going to be 0 meters per second. So delta V of our head is going to be equal to 0 minus 10. And this is in the positive direction, we're going to say, from left to right. So delta means V final minus V initial. So we have a negative delta V. Okay, it's just yet, but let's say in a 1950s car, or even my 1972, let's make it more fun. Or, oh, even more fun we'll do in the, excuse me, the Dr. H 1960 bus, standard microbus, that's officially called. Let's say delta t is going to be 100 milliseconds, 0.100 seconds. It's going to go pretty fast, right? So we say F equals m delta v over 0.1 seconds. And let's say we have negative 10 meters per second divided by 0.1 seconds. So that's 50, that's 500 newtons. Well, that's 500 apples. The weight of 500 apples. And of course it's negative because it's got a, I'm going to the right, it's got to push me to the left. So probably if somebody took 500 apples and made them a bit smaller, like the surface contact area of my head on the steering wheel, and especially the bus, it's got a metal dashboard, and I probably would hit the, since the steering wheel is horizontal, I would probably hit the glass, but I would go right through it. But let's assume I'm going to hit a hard object. Probably I'm not going to live. But now, let's take our 2020, I don't know what's the hot cars nowadays. I suppose the new Corvette, maybe it's the 2021 mid-engine Corvette, which I think is called a C9, or is it up to a C10? Now that has an airbag. So as soon as I hit the wall, the airbag pops out, like it pops out in milliseconds, really, really fast. It uses an explosive. That's why occasionally you hear stories about airbag factories blowing up. So basically, as soon as the car notices that it's got this huge delta V, the car itself, the airbag blows out. And now my head hits the airbag, and the airbag is big, right? So there's like half a meter between me and the steering wheel, but the airbag is now occupying that space. And let's say now the delta t now is equal to 1 second. So now we do the same numbers, 5.0 kgs and minus 10 meters per second. And we divide it by 1 second now. And now it's only 50 newtons. 50 apples. So now we have a much greater chance of living through the experience. And this is why you have padded dashboards and padded steering wheels and airbags. In fact, I would say that the delta t is probably more than 1 second, because the airbag the force from the airbag is not constant, because as soon as you hit it, you start squeezing it. Think about squeezing a balloon. And when you squeeze a balloon, it squishes out somewhere else, but the airbag doesn't stretch. So as soon as you start pressing on the airbag, it pushes back. So in fact, the delta t is longer. and the force then becomes small, and it does grow a little bit as the pressure grows, but it's nothing. It's probably not up to, well, 50. It might be. I mean, I don't really. I'd have to look at real numbers, but the point is that the whole idea of the airbag is to increase delta T so that the force decreases, so that more of us live through accidents. And as a side note, the problem with it is that as soon as people get used to these things, like I remember anti-lock brakes came along and all of a sudden road deaths went down. But then within a couple of years, the road deaths went back up again because people just they just felt, they knew that the anti-lock brakes were there, even if it was just in their subconscious mind. So then they just took greater chances. So now you had, instead of having accidents at 30, 40, 50 miles an hour, now you have accidents at 50, 60, 70 miles an hour because the drivers felt safer. And in fact, this same Corvette, and lots of cars have this, like Porsches were the first ones. The computer is constantly sensing what's going on, and it helps keep you from spinning out, for example, because I watched Jay Leno with the guy that was in charge of developing the mid-engine Corvette, and they both took a test. They did a road race. They went to a test track together, and they drove an older Corvette and a newer one. And the guy was telling Jay Leno that, I remember your face, that you were scared when you drove the older car at 150 miles an hour, but in the Corvette, you just don't feel it at all because it compensates for all the mistakes. Like when I drive my Scout, when I come to a hard curve on the freeway, I notice everybody around. I watch the people in front of me. They go in fast and they pass me because I'm slowing down, and then they hit the brakes in the curve. Back in the day, in a 1960s or 70 car, if you did that, your car would spin out. And especially hot cars like Pontiac Firebirds and things like that. You can't hit the brakes or even let go of the gas in a curve on these powerful cars. You have to actually be hitting the gas when you in the curve. So I grew up with cars like that. So when I'm coming into a curve, and the same with motorcycles, I have a motorcycle license. You're not ever supposed to hit your brakes in a curve. It's dangerous, and you should never let go of the accelerator in a curve. You always want to be accelerating. You want to slow down before you get to the curve, and then you want to hit the gas while you're in the curve. And that's all based on old cars and the older technologies. All right, let me look at my list here. We're almost ready. So has everybody gotten, let's say, all the different pages? Anybody need me to go back? No one has said anything. And then, by the way, the schedule calls for us to be doing the ballistic pendulum lab. And on Sunday, when I was setting up the pre-lab, I realized that I couldn't depend on you guys knowing what momentum and kinetic energy were, and what elastic and inelastic collisions are. And and also because we have to use a ballistic pendulum sim, the mechanism that they give us for a ballistic pendulum is pretty clever, but we don't have a way to reproduce that when we're staying at home. So we absolutely need to know what elastic and inelastic collisions are to help us understand the ballistic pendulum. And we absolutely have to know what momentum and kinetic energy are. So then I remembered this sim, and we don't have to do it in quite the way that I would expect a 2100 student to do, but we can do it enough to just understand some basic principles. Okay, so now we come down to the most important definitions to the lab, and it's conservation of momentum. And conservation of momentum is, these are one of these mysteries about the world around us that are very cool. And why is it that the world does these things? But it makes the world interesting place, but it also means the world has predictability. If the world wasn't predictable, we wouldn't be here, right? There'd be no, if you think of Darwin and survive, what is it? Evolution, survival of the fittest, human beings, there would be no survival benefit to being intelligent. Because we can learn how to throw a spear and have the spear land in the same place every time, so we can actually kill something from a distance, is a big deal. And so that meant that if you were able to figure out how to do that, or figure out how to make a better spear, and that is a cool thing called an axlatl or something like that. I'll have to show you that sometime. And then, of course, then you move on to a bow and arrow. If the world wasn't predictable, there'd be no reason to become intelligent. So it wouldn't be a survival trait. So what conservation means is that conservation just means that something is conserved, that means that it stays constant. And in fact, in this case, we have to really, people don't add this word, but it's there. It's conservation of total momentum. That way it covers all the situations. So that basically says that P total, well, let's see, this is a lowercase. Yep. P total and initial is going to equal to P total final. Now, of course, if I just set two marbles rolling next to each other, it's not a very interesting system. But if we look at collisions, it becomes much more interesting. But first of all, let's spell this out. So we're basically going to deal with a two object system. And so we have a momentum for object 1, and that's initial. And we'll have a momentum initial for object 2, and we can add them together, and that gets us P total initial and then we can have some later time, and so we can have P1 final plus P2 final will equal P total final. And as I said, if we just have two marbles and we roll them down a ramp, that's, well, yeah, big whoop. Of course, give me a minute. I forgot something. This is when no external force. Yeah, sorry. So if there's no external force, and that could be gravity, and that could be pushing something, This holds true. Forgot, sorry. Of course, because I just realized if I roll the marbles down the ramp, they're going to increase in momentum. Oops. But you knew that, of course. So if I roll 2 marbles across the table and there's no friction, which is an external force, the total momentum will stay constant. But this, of course, is kind of a boring situation. What's really fun are collisions. Whoops. And in a collision, you'll have object 1 and object 2. This will have a positive momentum initial. This one will have a negative momentum initial. Now afterwards, we don't know, but we'll see. So if we take these two guys, we put them together, then that says that if we sum together the initials plus, and then we can set them equal to the sum of the finals. And we just always remember, don't forget the pluses and minuses. Oh, my phone is pestering me. What does it want? Oh. Oh, oh boy. Telemarketers are us. I hate when they hit me with text messages. At least Android has this. I can just hit a block on a message so I don't hear from them anymore. So I forgot to make a duplicate here, but let's just copy this. Now, oh yeah, one final thing. It turns out that momentum is always conserved. No matter what happens, momentum is always conserved. It's always constant. Total momentum.
I have a question.
Sure.
All right, so I'm a little confused. So we're calculating conserves momentum, and then it's different from total momentum.
No. Conserved conserved just merely means that it's constant. That's it.
Uh-huh.
So you calculate the total momentum at the beginning, you calculate the total momentum at the end, and they will equal each other.
Always, right?
Yeah, that's right. I mean, you have friction in the real world, but like when I'm telling you, when we do particle collisions, so there's no friction there, it always holds true. I calculate all the momentum of all the particles coming in and all the particles coming out. It's always conserved. Always. It's amazing.
And in inelastic,
Yeah, that's correct.
one after is gonna be the same.
Yeah, isn't that a trip? Yep, that was, yeah. In principle, you notice that in the pre-lab, but that's absolutely right.
Thank you.
You're welcome. That's fine. It's a great question. Conserved is just a concept, and total momentum is the thing you calculate. And the point is, like, if you know P1 initial, P2 initial, And if you know P1 final, you can figure out what is P2 final, because you can depend on the conservation. And so if I do a particle physics collision of two protons, and I know the momentum's coming in, and I can't, there's a missing particle, I can depend on the conservation of momentum to tell me that the missing particle must have had this momentum, for example. So for us in the everyday world, it's not, is it, well, it makes some difference, because it, when you crash together two cars, it's actually an inelastic collision, or partially inelastic collision. Um, so it'll give you some insight as to why cars, when they hit each other, if you look at skid marks on a road, I guess, it's not, and maybe, if you were going into criminal justice, and then maybe you got, or if you went into policing, or even car insurance people might need to know something about how the cars behave when they hit each other. So it might become useful in the real world there. The most important real world application of momentum is, again, the F delta T equals M delta V. That you see that, you face that all the time. Walking shoes, soft padded walking shoes, all those things. If you buy a better car seat, better padding in the car seat. Okay. New slide. Hopefully it's still there. Yeah. Okay, so the next one we have to be a little careful about. So there's this other one called conservation of energy. Now, conservation of energy is also always true. And just hold on a minute, Juan. I just finished saying, you sort of were thinking about the assignment. You're going to go, well, wait a minute. We just learned that, right? But just hold on for a minute. This is conservation of energy, but remember, there's mechanical energy, there's chemical energy, and thermal. There's all kinds of different forms of energy. So that says that in before and after, the total energy is the same. But these two, for example, are pretty hard to see with our eyes. We need special instruments, where the mechanical energy is very obvious. So for us, we are using the conservation of mechanical energy. Remember I said earlier, that's another way to think of kinetic energy. Conservation of kinetic energy. So because I noticed that the lab manuals and the textbooks aren't always careful about this, because this is always true. This is a fundamental property of nature. Energy can neither be created or destroyed. Mass. Einstein demonstrated that with his famous equation. And in fact, what he said, he actually wrote it like this. People don't commonly know that, but his idea was that mass is not just about how many molecules there are, but you need to take into account the energy too. But that's a different class. This is always conserved. Whatever total energy you had at the beginning goes somewhere. It doesn't disappear. So it might go, if it's friction, a car rolling down the road, it eventually comes to a stop. So it had a certain kinetic energy at the beginning, and then it went to zero kinetic energy. So the kinetic energy wasn't conserved, but the total energy is not always conserved. Because energy can be converted to different forms, but it can never disappear. It's always out there. In fact, when we take two protons and we slam them together, we actually get particles coming out that are much heavier than the sum of the two protons, because we have to take into account the energy that we're slamming the two protons together. So we convert the masses of the two protons into energy. We add in the kinetic energy of the two protons when they're coming in really fast. Then we get a certain amount of total energy. So we can produce a particle, as heavy as the total energy divided by c squared. That's a pretty heavy duty thing if you think about it. We can create heavier objects simply because we've put all this energy together in one place. So what happens then is we can't depend on mechanical energy being conserved, so we have to pay attention. But what then is, it leads us to, for our collisions, the final definitions for collision. So in elastic collision, we have momentum is conserved. And KE total, or KE is conserved. So momentum total, KE total is conserved. And in an inelastic, momentum total is conserved because it's always conserved. And KE, no. And there's a thing called a totally inelastic collision, which becomes easier. A totally inelastic is inelastic is when they stick. Inelastic simply means that let's say that they touch for a t not equal to 0. And in an elastic collision, we just say that the time that they touch each other is basically 0. I mean, it can't be. That's an interesting question, because when I think of F delta T and the delta P, that means that I got to think about that one and how to relate it. But in a short form, the time that they're touching each other is basically 0. In an inelastic collision, it's not equal to 0. And then basically totally inelastic, the touch T equals infinity. If you think about it, they stick together forever. And then there's the so-called explosion, and we'll think about that one as we do some examination of these things. Notice with all of these, even though there is a force, remember I said earlier, part of the definition of the conservation is no external force. And that is true here. the only force is what they exert on each other when they collide. What do we got? We have 13 minutes plus about 25 minutes, about a little more than a half an hour. Okay. So if you're finished with your notes, let's open up a spreadsheet. If you're not able, if you haven't successfully gotten Excel going on, and in fact, I have to double check that I thought I made an assignment for it. I hope I remembered. I knew there was something, one of my classes, there was an issue. It's not a crisis if you have to use Google Sheets for this. Let's see. So maybe, oops, so it was you guys. I'm sorry. Did I import it? Crap. Okay, I screwed up again. So, what should I do? We're not going to do, well, we're not going to do any fitting here. So if you have the ability to open a Microsoft Excel spreadsheet, please do. If you can't, that you can open yourself up a Google Sheet. That'll work just fine.